All right, so guys, so what we are going to do today is I'm going to use this exercise to review what we did last time about the electric potential energy, potential difference, and how can you calculate energy from potential. Sounds good? All right, so I think this is a very, very good uh, exercise because it's pretty much like sum up everything that we have done in one problem here. All right. And more than that, actually, I think this is going to look pretty close to what is going to be asked in the exam because what else do I ask? All right. But anyway, so I will post extra homework very soon for you to be able to practice a little bit more advanced problems. And that will be the kind of question that will show up in the exam. Okay. So let's try this one, guys. So in the rectangle of the figure, the sides have length given. Okay, so you have the width of 5 centimeter, the length of 15 centimeter. Q1 is negative 5 microcoulomb. The Q2 is 2 positive microcoulomb. And set V to be 0 at infinity as usual, because that's what we have been doing. That means that allow us to use the expression of V equal to KQ over R. So this one is good. So what is the electric potential at the corner A and B? So let's try the first question first, shall we? Because this is going to be the easy one to try. And it's just the question of finding out the electric potential from charge distribution. Yeah, sounds good. All right, so let's attack problem A. So what you have over here is, of course, you're going to use just the expression of KQ over R. So I would say the potential, so let me call it a total potential at A, is going to be the potential that's coming from Q1. So let me do the highlighting here. So this is what it is. So I'm trying to draw the inference over here. So the negative Q1 will generate or give you the potential at A equal to what? What I no problem is a K, the charge generating that potential divided by the separation from that charge to the position of calculation, which is in this case is 15 centimeter. All right, so let me put 0.15 right here. Sounds cool? All right, and then you said I have one more over here, Q2 will influence this much. Okay, so you say, okay, all right, let me highlight this one as a yellow, plus K, the Q2 divided by the distance from charge to the location of calculation here is 5 centimeter. So let me put 0.05 meter right there. And that is the blue one. That's it. Okay, so this is a good review here. This is how easy it is to calculate the potential from charge distribution. You just keep doing the KQ over R, KQ over R, KQ over R, and sum them up. All right. The only thing that you have to be careful with is the sign. If Q1 is negative, so don't forget to put the negative sign in there. So let me do a quick substitution here for you guys to see, divided by 0.15. Cool. All right. And for Q2 is positive. So don't worry about that. So you just plug that thing in. Okay, let me omit the unit here. There you go. All right. So that's what it is. All right. Now, for this particular problem, I really want to do the numerical calculation here for you guys. So let me substitute everything in there. So there's a common factor K that I can pull out. So that's K. Okay. And I can work out these numbers here, I think. So let me think about it. It's 6 minus 5. So it's 1. So it's going to be 1 times 10 to the negative 3 divided by 0.15. Okay, just leave it there. It's positive at the end. So what it is, that means at location A, the net potential is positive. When you think of the potential, it's the same line as the potential energy. So when the potential is positive, it means you're going uphill. So at the location A, it's higher in potential. So if you think in terms of like geography, so it's just like it's uphill at A. It's higher. It's elevated. Okay, sounds good? Okay. All right, let's do the net potential at B, shall we? All right, so now you start to get the feeling of how it goes. So you get, no problem, at B, So let's start from the influence from Q1. So it's going to be K, Q1 now. The distance over here is 5. So just put 0.05 right there. Plus, now the influence from Q2 is right there. Okay. So that one will give you K, Q2 over 0.15. All right. So number looks almost the same. So over here, I can pull out the common factor K. So let me do this. Numbers over here. Q1 is negative 5 micro 10 to the negative 3 divided by 0.05 plus the Q2 is positive, so it's 2 times 10 to the negative 3 divided by 0.15 right there. Cool. So you guys still following so far so good? All right. So I'm just going to leave K there, even though you can substitute K to be like 9 times 10 to the 9 on and on. But I mean, it's just a number. So I don't worry too much about it. So over here, what I have is, okay, 3 is 15 minus 15. So it's going to be negative 13 times 10 to the negative 3 over 0.15. All right. I don't worry too much about the final numerical value over here. But what I really want to show you is at B, see, the net potential is negative. So you can imagine that at point B, you are sort of like going under. Okay, so if you say 0 is your ground level, A is elevated, is higher, and B is sort of like you're going downhill a little bit. So it's below the ground level. Sounds cool? All right, and that's it. So that's how you calculate the net potential at one particular point from charge distribution. Nice. So far, so good? All right, good. Still like, okay, you guys still have some energy left, right? For one more week? Okay. All right, now, so we're done with the corner A and corner B. So what's next? Now, C, here's this is the main question for this particular problem here. How much work is required to move a charge? Third one, the Q3. So you have one more charge. So I can probably just have, charge number 3 waiting. But you want to drag or you want to move from B, starting from here, to A. You want to end up there in the diagonal rectangle. So you're going to drag it up here diagonally there. So the question is, how much work do you need, okay, to move charge number 3? So it's mean, okay, so I'm going to place charge Q3 right there. I'm going to drag this one all the way up here. Guys, so what do you think? And here comes the connections between the energy and the potential. We already said it's easy. Once you know the potential difference, the potential difference. So part C, the delta V between point B and A, right? Because that's when you want to go from B to A. And every time we talk about delta, right? Remember, delta is final minus initial all the time. We use this since like thermodynamics. So that means you're going to take the potential at the final position A, and you're subtracting by the potential at the initial point B, because you're starting from B. But the VA and VB you already calculated here. So VA is right there. That's from part A. VB, that's from part B. So you are able to calculate the potential difference from B to A very easily. Cool? And as you can see, if you substitute the numbers there, so you just plug in the number here, bam, you plug in the number here, bam. At the end, you still end up with positive. Actually, I can do that number right now. So what you have over here is K, 1 times 10 to the negative 3 over 1.15. And then you subtracting the negative, see this, K, 13 times 10 to negative 3 over 0.15. Cool? All right, so you're subtracting the negative value. So eventually they are adding. So at the end, you get what? 14. All right, 14 times 10 to the negative 3 over 0.15 volt. That's it. That is the potential difference between the two. And do you notice something here? The net is positive. The potential difference is positive. Does that make sense to you? But yeah, John, that makes sense because we just said at point B, it's below ground. At point A, it's higher above the ground. So think about it. If you think in the mechanical picture, you want to drag something from below to to the top. I mean, you want to drag something uphill, you're going to have to supply some energy to it. And in this case, you're going through potential. Potential is positive. So it means you are trying to climb the hill. You're climbing up the hill. You want to go up to a higher potential. That's why the potential difference is positive. Now, the final step, how much energy do I need? So the energy supply is must be equal to the work that you need to go through, right? You want to have the work done. You have to bring the charge Q3 from B to A. So the amount of work done, you just said, it just take the charge Q3 and multiply by the potential difference between the two. That is the amount of energy that required for you to move between 2 points. Cool. All right. And that's it, guys. It's done. So I can put the external sign over here. Just for those of you that really, into this kind of whole business of definition of whole thing, will agree with me, because in thermodynamics, if you want to talk to about the W of the system, and you can try to calculate the energy, the relationship between them must have a negative sign, right? Remember from the first law of thermodynamics. Or on the other hand, if you flip the sign, your work done is going to be the work done by external force, on and on. So everything is good. So over here, that's it. So all you need to do is just take the Q3, 3 microcoulomb, and multiply by whatever numbers that you just got up there, and you're done. That's it. So it's a 3 microcoulomb and multiply by the delta VBA, which is just this number right here. And that's it. You are pretty much done. Cool. You guys still with me, right? Okay, the sound effect is back. Okay. Ooh. Cool. You like this problem here? I think that summarized things very well. And just to make things sort of, I think, I hope it will help even better. Why don't you go back to the PHET Colorado physics simulation? Okay, let me give you the direct link to that particular simulation. It's about electricity and magnetism there. So let's see if I have that here, charge and field. Okay, here we go. All right, so if you want, you can also check this one out. But if not, you can just watch me doing it. So this is the simulation that we used before. So let me take you guys there. Okay, let me grab this chat. Where's the chat? Here. Okay, here we go. All right. So what I'm going to do is I'm going to simulate what we just did, okay, with the previous problem there. What we have was you have a rectangle, 2 charges at the corner. So what I'm going to show you, and it's going to look pretty much the same, is, all right, so I'm going to take charge at the corner that is negative. Am I right? So let me double check. Where is it? There we go. All right, so it's had a negative 5, and at Q2 is positive 2. So I'm gonna do the same ratio over there. So it's negative 5. So let me sort of like put 5 of this here, even though it's nano, but let's assume that that's somewhere there. So that's about that's exactly negative 5. Okay, that's negative 5. So I need to put 2 right here. There you go. So that's it. I have negative 2. So from what you're seeing over here, okay, let me do scaling a little bit better here. So that's, okay, that's more like a rectangle that we were looking at. And now what I'm going to do is I'm going to turn on here, voltage on the right there. You see that? So what you can see over here is the blue representing the negative value, the red representing something positive. So it means the blue, you can think of it as like a below ground, and the red is above the ground. Cool. And what we were looking at is, let me put here, I have a meter that I can drag here. And see this? So if I place at the upper right corner over there, that's the positive potential right there. It's reading 3.373 volt, on and on. Is probably pretty close to what we have And if I move to what the lower left corner there, it's in the blue territory there. It's negative. See? So you can imagine from this one, it's like, okay, Ajahn, you're going from the lower left corner and you want to drag things diagonally to the upper right corner. You're going uphill because you're going in a higher potential area. And this one, that's exactly, well, I don't think this one, where are you? No, great, no. All right, so so what I'm gonna actually help you visualize things even better. All right, so right now the simulation give you the green, the blue and the red. This simulation can also write the equipotential line. So let me do that. Here we go, and I hope this will reveal something that's help you visualize things a little bit better. Here we go. There you go. There you go. Let me. Oh, did I? What did I do? Oh shoot! How come it resets? Sorry. All right, so let me redo this one quickly. 3, 4, 5. Oh shoot, that's negative. Sorry. 1, 2, 3, 4, 5, and 1, 2. Here we go. Voltage. Equipotential surface. Bam. Okay. Bam. Bam. So this one will look kind of like resemblance of the altitude map. Does that help? Okay, let me add one more here. See? All right. So I hope this kind of like give you an overall idea. I can more. It looks nice. It's kind of having fun doing this. Okay. So this one is like altitude map. And actually I can turn on the value over here. And this is exactly if you can look at the like altitude map and you look at like, you know, it's a two-dimensional plot of like a geographic map or something like, hey, where is the height of the mountain? And as you can see, the blue is going to be like an abyss. It's going like into like super, super deep. And there's the deep hole right there. And the red is the top of the hill. Okay. So when you want to go from the lower left corner, that's a negative one. Yeah. And then you kind of climb uphill all the way to the upper right corner. And that is going to be the positive potential. Does this help? I don't know. I hope this give you a like an overall picture of what we have been doing in the past 2 weeks. And if you look very carefully, I want to emphasize one more time. See, this agree with everything that we have learned. At any point on this line, the directions of the electric field must be going in the direction that is perpendicular to this line. Remember we mentioned about this one when we were talking about the field and the potential. In the gravity, under gravity, field is pointing down. When you cut the field perpendicularly, you get a level. And that level, no matter where you are on that level, you're sharing the same potential energy. It's the same idea. Or you can think backward now. If you have a level that's sharing the same value of the potential, you cut that perpendicularly, you should get the direction of the field. Cool? Okay. Okay, so that is the connection between the two. So if you look in this whole map over here, no matter where you look at, you will see that the potential and the field line or the field vector always perpendicular to each other. Yeah, isn't that nice? Okay. So if you like the material, just, you know, press the like button. Okay. Okay. All right. But I think this is a very beautiful structure of, well, I would say this is the structure of our universe or our nature over here. And okay, once again, I don't want you guys to go overboard or anything here. This is the theory that physicists came up with explaining the electric phenomena in our nature. Okay, I just want to confirm that point because, well, electric field, well, you can say, I don't know, it's not real or real. Who, I mean, we can argue until the day we die. Or what about the concepts about like, electric field lines? Is there any lines or not? I don't know. What about the potential and potential energy? That's everything that comes up based on physics theory, all right? But it seems to work really well, and it's allow us to explain things that are happening in nature. And once we sort of like, okay, sort of we have been using this theory for a long, long time, a couple hundred years, then it seems like, yeah, that seems to be a working structure of our universe. And then now we can say that, okay, the universe is kind of beautiful. It has some structure in it, on and on. Cool. All right, guys. So I hope this summarized everything that we have learned about. So now we conclude, right? We have four things pretty much. Okay, the field and the force. They come in pair, hand in hand. Once you know the field, you definitely know the force. Place a charge in that, you're done. Okay. And the second pair is the potential and potential energy. Okay, it's easy as well. Once you have the charge going through some potential energy, you take that charge, multiply by the potential difference, you get the energy. So the name is just kind of annoying. One is called potential, and the other one is called potential energy. You just dropped the word energy, you get to the potential. That's too bad. Nice. All right, guys. So that's pretty much the conclusion of things that we have done here. However, this is what we have left for you. All right. So it wouldn't be nice if I'm not talking about some calculus. And this is something that is very, very nice to have. And it's simple enough, I think, to include this portion into in our lecture. The reason is because you will see, even though you don't understand anything at all, but you will be able to do it. And once you do it for a couple of times, then you will be able to come back and understand it at the end. All right, so I'll show you what it means by this. I'm not sure if this is a good slide to sort of give you the whole idea, because it's talking under the topics of electric fields and electric potential. So it might be, well, I would say it's contaminated by physics already. So I think maybe it's easier for me to show you based on just pure math, all right, from the mathematical perspective first. And after that, we'll come back to this slide and conclude everything. Sounds like a good plan? Okay. Okay. All right. So what I'm going to do is this. I'm going to show you some very simple thing. And I just want to check if you agree with what I'm trying to write right now. So if I have some function, okay, let me draw that. Let me say the function is very simple, guys. The function that I have is just y equal to x. So everyone kind of know, John, this is a straight line. So that's no big deal. Okay, so this one is fine. But then things get more interesting if I want to do more than one variable. So that's means I'm going to extend to this. Let's say z. So now I'm going to do two variable function. Okay, so that means at this point, so I'm talking about you're going to have like a three-dimensional something going on, right? The z is your third axis, and now xy is going to be your two variables. Okay, so at this point, you can imagine that if I draw this one as an x, that one as an y, the z is pointing to your face, perpendicular to the screen at this point. Okay, now I want to do the same function, x, again. I haven't done anything. It's still a straight line anyway, okay? But it's a straight line in the three-dimensional space now. So that means if you draw something like this, that you are seeing over here, z is hitting your face, right now. Z is hitting your face. So y equal to x. When you look from the z axis downward, like what we are looking at right now, you're not going to see anything. Right? But what I can do is I just did what we just did. I'm just going to do what we just did with the potential. What I can do is I can just give you a line. When x equal to 1, when you look from the top down, I need a line here. Here we go. That's x equal, let me use different color. X equal to 1, x equal to 2, x equal to 3, x equal to 4. What I can do is I can label this. That's 1, 2, 3, 4. You see what I'm saying over here? I don't know, does that help? So one more time. So if I look sideways, so this means if I plot X and now I tilt the Z to pointing up. So it means in this case, Y is point into the page. Does that make sense? I mean, I should have like a 3-dimensional plotting more than just this, but I think this is easy enough for you to see. So if I tilt the coordinates axis X, Y, Z and make the Z pointing up, X still pointing to your right. So this one, you can still see that it's going to be a straight line like this. Does that make sense now? Okay. But then when you look top down, when you want to look from the top down, so this is your eyes, you want to watch this curve downward, it will look like the figure on the left. Does that make sense? So it's a wedge. มันเป็นริมนะ it's like a wedge, like a wedge when you look sideways. So this is a wedge like that. But when you look top down, I mean, you just like, you look at the top surface of a wedge, you don't see anything. But if I draw the line on the wedge, you can see that, hey, this is X equal to 1. That's X equal to 2. That's X equal to 3. That's X equal to 4, right? Over here. But when you look top down, I can draw this line right there. 1, 2, 3, 4. Cool. All right, you guys with me, I hope. All right. Wow. I think I remember I used to have a better tools than this one. when I was teaching like calculus, I think I do like a 3D plotting software. It's like, oh, this is like so primitive here. But anyway, sorry about when I'm doing physics, it's like everything everything go downhill. It's like super primitive over here. All right, but anyway, so here's the operation I want to do. Okay, so what I'm going to show you is this. I'm going to do the derivative just like what we did, but now it's going to be partial derivative with respect to X. The reason I have to do partial derivative because I have also Y variable here, even though Y does not show up, but it's there. I mean, there in the sense that it's 3-dimensional plot. So over here, it's 1. Everyone knows what tan is 1. dy, dz by dx is definitely 1. But then what is interesting is this, guys. What does this derivative is meaning? What it means is z is changing with respect to x equal to 1. The rate of change. That's what the derivative is trying to tell you, right? The meaning of derivative is just a change. So change with the rate of 1. So it means every time you move x by 1, z will increase by 1. That's why you get a 45-degree lines over here. That's perfect. But now there is a better information than just number 1. It turns out, you know that every time that you move sideways to your right by 1, your z increase by 1. So if you move 1 more of x to 2, your z will increase to 1 more. So that's why you get 2. If you step to your right 1 more step to 3, z will increase 1 more to 3. Does that make sense? So actually, it turns out number 1 right here not only give you the magnitude of the change in z, but it also give you, wait for it, okay, the direction. What it's saying over here is the directional change of this is in the positive x direction. Does that make sense? So what it means is actually I can turn this into a vector. And I would say this is the change that is going in the I direction. So that means not only I get the number 1, but I also saying that if I to do the derivative with respect to x, whatever the change that is happening is going to happening in that coordinates axis x, which is the I, is the direction in along the x. So does this give you an idea? So that means I already get a directional change of my function over here. But then when you look it one more time, Ajahn, very tempting. See, from the look of it, by doing just simple derivative like this, you get something that actually already perpendicular in direction with respect to the level. These lines give you the level that we have been talking about. So that is the clue that I'm trying to give to you is simple from now on. If you have a function and you take that function and you take the derivative with respect to the direction, in this case, with respect to x, you will get both the numbers, which give you the rate of change, plus you will get the directions of that change along the coordinate variable that you use in your derivative. In this case is x. Cool? But then this is exactly what we want. Now we can imagine that this is your potential level. This is a V, potential level. And the E, I mean, this arrow over here, this is what you want. You want this to be electric field, right? The only thing that is different is we define the electric field to be pointing downward, not upward. We said electric field always point from high to low, like gravitational field pointing down. Up is high, down is low. So gravitational field is pointing downward. Same thing with the electric field. Wherever electric field pointing to is pointing toward the lower potential. But definition of the calculus, every time you do derivative, it means increasing, right? It's a rate of change in the positive sense. So that's why the only thing that we need is to just flip the sign to get to the E. So this is not the E that we want. The E that we actually want, not this one, but it's going to have an opposite effect of this. So all I care about for the E is now, Ajahn, you flip that one. So in conclusion, what I have here is if you want to calculate the electric field, all you need to do is just do the negative of the derivative of that potential function with respect to the coordinates that you want to find the change. Does that make sense? But because this one is we are doing everything in one dimensional, so what you have over here is, all right, it's a vector, but it's a vector in the x direction. So okay, that's the x direction. So in the future, if you have like a super full, like, you know, three-dimensional function on and on, you can figure out the electric fields in the y direction. What are you going to do? You take the z with respect to y. And that's it. That will give you the perfect electric field vector. Because you already knew the components of electric field in x, is simply take the negative derivative of z with respect to x. You want the y components, you take the negative derivative of x, of the function with respect to y, on and on. Does that help? All right. So if you don't get this one, or I mean, my explanation is kind of like take you too far, this is it. This is the conclusion. And I hope you understand this red box much more easily here by just saying that if I want the x components of my electric field is a vector, right? So what I do is just I take the potential function and do the derivative with respect to x and then put the negative sign in the front. Bam, I'm done. Seriously. And if I want a y component, I take the v derivative with respect to y, slap in the negative sign, I get the y components of my electric field. And if you have like a full like three-dimensional potential function, you do the same with the v, take derivative with respect to z, slap in the negative sign. Oh, this is a typo here. It's supposed to be z. You get the z component of the electric field. And you are pretty much done.
Okay.
All right. And this is a conclusion on the right. By doing this operation, you automatically link or connect the potential function and the electric field vector. This is so cool. All right. And for those of you that have already taken calculus 4, I keep mentioning calculus 4. I don't know do they exist or not. But anyway, if you have already taken this calculus 4, this operation is called gradient of a vector or a gradient of a function, actually. It's a gradient of a function is when you take the function and then you do the derivative with respect to each coordinate axis, and then you get the vector that points perpendicular to the level automatically. Yeah, so that's what it is. Perpendicular, 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 perpendicular. See? So mathematical tools are already ready for us. All right. And actually it works with any coordinate system. But as I said, I don't want to take you to sort of like, deal with like spherical coordinates on and on. So don't worry about that. All right. But anyway, in conclusion, this is pretty much like a recipe for you if you want to connect between the potential function V and the electric field vector. How easy it is to connect them is just simply doing this operations here. Okay, I'll show you how it works and you will see like it's super easy. Here we go. And maybe the question in the final exam will look just like this. So as I said, even though you don't understand the mathematics at this point, don't worry about it because at least you get a feel of what this operation is trying to connect. It's connecting the potential function, which is purely scalar quantities, to the electric field vector. So this operation allow you to figure out the electric field vector from a potential function. I'll show you right now. They say calculate the electric field from this electric potential described by this function. But อาจารย์ it's simple. I want x component of this. What I do, negative dv by dx. That's simple. Let's do this together. Negative sign is there. Everyone still remember how to do partial derivative. When you try to do the partial derivative with respect to x, you treat y as just a constant. So what you have over here is 2xy plus 0 plus z. Cool? And that's it. You already got the x components of electric field. What about y components? You do the negative dv by dy. You do the derivative with respect to y, you get x squared plus 3y squared plus 0. See? You treat x and z to be just a number. What about the z component of this? You do negative dv by dz. The first term is gone, there's no z in it. The second term is gone, there's no z in it. The last one, you get x. And that's it, guys. It's done. So you can actually wrap this thing up into a vector form. So your net electric field vector is just Ex along the x direction, Ey along the j direction, Ez along the z direction. And now you got the function, right? You are able to calculate or evaluate at some point. For example, if I บอก อาจารย์ I want to know what is the electric field vector at 111, for example. So this means you would sort of like, hey, I am located at 111. I want to know what is the electric field at this point. So all you need to do is just plug in 111 for the x, y, and z values. So what you're going to get is just I plug in the 1, I get 2, 3. So it's a negative 3i. I put 1 in there, I get 4. So it's a negative 4j. I put 1 in there, I get a negative 1k. And that's it. That is my electric field vector at 111, something like that. Okay. Cool. And from this point on, you can calculate if you want to find the magnitude of E at 111. All you have to do is just, okay, you do Pythagorean theorem, negative 3 square plus negative 4 square plus negative 1 square. So you'll be able to trace back to get to the magnitude of this electric field at whatever point that you want. And your job is done. Cool. Sounds good? All right, so I hope this is like a very easy addition to stuff that we have already learned. And I think it's something that, you can slap in and then allow you to at least get to know the gradient operation, or at least you can see that, all right, the derivatives in higher dimensions have the underlying connection between the scalar function and the vector that's point perpendicular to the level from that function. So that's kind of nice. Nice to know. And I already sort of like determined that the level of difficulty is pretty low, even though the underlying principle from math is maybe more complicated, but in terms of the operation or the way that you have to actually perform the calculation is simple, right? So let's do final one, guys, and then I think we can sort of like close down this handouts over here. So let's say over here now you have electric potential function. Now it's two dimension. I mean, just have only two variables, x and y. So it's even better. So you don't have to worry about the z directions. So it's only x and y. In unit vector notation, what is the electric field at particular point? See, I would redo it again. It actually is even easier because you only have x and y components. And when you say in the unit vector notation, it means it's an ijk. However, in real exam, I don't think I'm gonna require you to do any particular notation. So you just pick whatever your notation that you prefer. You can do a bracket style. You can do, you know, IJK style. You can do like a matrix-like style. Up to you, right? Whatever you prefer. So over here, you want to calculate the x components of the v. You do the negative dv by dx. And this is negative sign is there. Derivative with respect to x, you get 2x. So I have 2 times 2x. That's it. Okay, the second terms disappear. So for the y component, you do the negative dv by dy. So it's a negative. So there's a negative again. That's a negative 3 in the front. And then you do the derivative of y squared, you get 2y. All right, works. And that's it. So if I want to put it in the unit vector notation, it will look like negative 4xi plus 6yj. And now you want to evaluate this vector at 3, 2. Just plug in the value. You get negative 12i plus 12j. And if you want, you can find the magnitude of this one is going to be 12 root 2. And you are done.
Okay.
Cool. All right, guys. So that is it for this particular handout here. And I already posted the handout number, I think it's number 9 on the Google Classroom. So just download that one during the break. And we'll take 15 and I'll see you at 11 and we're going to continue on. Sounds cool? All right, guys. So let's take a break right here. Okay, so what we are looking at next is going to be I would say the highlight of the course. The reason is because I think it's the newest stuff that you might have not heard before. Plus, it used kind of like advanced calculus in the sense that it needs a little bit of connections to a couple of things that you have learned, plus some new thing, plus some vector calculus, even though we're not going to dive too deep into that one, but it's just something that's like a lot of combinations and everything wrapped under something that we call Gauss's law. Okay, so this is a very cool, cool law that's as like another way to explain the electric phenomena. But instead of having things described using the Coulomb's law, now we're going to have another approach. And that's another law that eventually they are equivalent. Okay, and this one is so good that allow you to unlock another approach for you to calculate electric field through the concept of electric flux. And once you have that, then we're going to take a look at the application of this. And the main application we're going to look at is going to be the capacitors. Okay, so that will unlock the way that you can calculate the size or the magnitude of some parameter that determines how big is a capacitor. That's going to be the business of what we're going to do next time. But for today, we are going to focus on this electric flux because I think this is going to be the hardest portion of the whole thing. Once you get a hang of this electric flux, the concepts that build the Gauss's law will be very, very straightforward, I would say. Okay, so that's why this is the main focus. If you understand flux, that's it. There's nothing else to it in the sense that you just slap in the sort of like maybe agreements or some sort of like the visualization tools around this already visualized under flux, and then you have Gauss's law at the end. Okay, so you know what I mean a little bit better when you understand what the flux is. So remember that we mentioned briefly when we were talking about the electric field lines, and then we were talking about, okay, let me sort of like draw a very, very rough sketch of what you saw before. So when you were seeing this back in the day of electric field lines, and we were discussing like, hey, Ajahn, the portion where the line density is high relative to the portion that the light density is low seems to indicate the strength of the electric field. Remember that one? Yeah. And I think everyone agree with me. This is going to be sort of like this is going to be low electric field strength. I'm sorry, high. Sorry, my bad, my bad. That's definitely not the case. High. This is high E. Okay, because the light density is high. And this is going to be the low electric field region, okay? So that means now we are going to take that into a quantitative analysis, okay? So we're going to take it ahead. How can we connect the line density to that electric field magnitude or the electric field strength that we were talking about? So the easiest and maybe the most straightforward way that we can define that is just, hey, assuming that you have a way to count the number of lines. Even though this is not real, you probably can say that, right? So this is definitely not going to be real, but it's the way that you can visualize in your head that there are some lines there. And all you have to do is just divide it by the area, because that's the density that you really want. And once you have that, this will somehow give you the electric field strength. So you can say that electric field strength is linearly related to the lines per unit area. The measure of that number of electric field lines, we call it electric flux. So you can, I think it's interchangeable to say about the number of lines, or you say electric flux, okay? So what you have over here is you can say, hey, there is flux going through a surface. It's the same thing as saying that there is some electric field lines penetrating that surface. Same thing, okay? To make things even easier, instead of introducing any extra constant to this, I'm just going to turn this proportional into just an equation and be done with it. All right? And that's it. We're just going to call this flux phi. That's the notation for it. Area, let's call it A. Electric field line is electric field strength is E. So you can rearrange this one and call the number of flux through any area is just a product between the electric field multiplied by the area, and you are done.
Okay.
So where is the complication? When you look at this one, it seems like, okay, Dan, I don't have any problem. You can count. I mean, of course, in reality, you're not counting it. But I mean, for this particular picture over here, just say, okay, 1, 2, 3, 4, 5, right? We can count. Here comes the question. What if I have an electric field line that doesn't really go straight through the surface in the perpendicular fashion like this? For example, I might have electric field piercing through like this. How are you going to count that? You see my point here? Because electric field line does not need to go through an area in the perpendicular fashion all the time. Yeah. So that's what we need here. This is the reason why we have the subscript over here. That is a perpendicular. So that's why we sometimes we call this a perp. So it's just the area that is perpendicular to the E. Or you can think backward. It's an E that is perpendicular to the A. So now here comes the question, but then wait a second. How are we going to deal with this? So one way to do that, and I think that's a very straightforward way, but then if you have electric field that's not going through in the direction that you want, all you have to do is just break this into two components. Why not? Doing just the vector decomposition, just like what you did before, and you're done. When they say you're done, okay, let me use different color, make it a little bit cleaner here. Let's go. Here we go. So that's one component. That's the other one component. And of course, once you break this into two components, the component that sort of like does not penetrating the area, you just discard that portion because that doesn't do any good. The only portion that you want is just a portion that actually going through the surface in the perpendicular fashion. Sounds cool? I think you get an idea what we're trying to do, right? However, there is still some difficulties. The reason is because sometimes it's not the electric field that you want to manipulate. You might want to manipulate the area instead because there's no restriction that you have to manipulate just the electric field. Sometimes electric field is already there. And then you somehow come up with the area that you want to analyze. How are we going to do that? Okay, so here comes the thing. This is possibility here. For example, you might have an electric field pointing down. And somehow the area of interest is somehow oriented in some angle with respect to that electric field. So now from the look of it, electric field pointing down looks nice and tidy already. You probably don't, I mean, you can, but you might not feel like you're not inclined to decompose the electric field, right? Because it's already down. It's kind of nice. So there is another way. You can do it in the opposite direction. Why don't we introduce area vector? Wow. Sounds good? So you already learned about the area to be just I think you learned since like maybe elementary school or whatever. Its area is the width times the length. There's no direction. But in reality, think about it. If I have a piece of paper over here, okay? Actually, this piece of paper has orientation, right? So if you think of the surface area of, it looks dirty here, but anyway. So if this area is the area of interest of yours, then this is pointing up. The area is facing up. This is facing you. This is facing left, facing right, on and on. So actually, you should be able to assign the direction to the area vector, to the area to make it an area vector. Isn't that cool? That's what we want. So what we really want is this. So if you look at the next slide over here, here we go. So if you have electric field is already oriented in some particular fashion, and you have an area that is not perpendicular to it per se. So what you can do is this. The way that we did was just like we assigned, here we go, like this. Oh, sorry, the bottom one. Look at the bottom one. We're going to assign the vector for that area by taking the direction that is perpendicular to the area itself. That's a vector. Oh, let's do the green here. There's a vector here. So if you have a piece of paper that I just have, the way that you assign the vector to this area is just having it perpendicularly upward or downward, up to you. This is open surface here. But at least you have to define the direction to be perpendicular to the plane of that area itself. Okay, so this is what you agree. And you will agree later that this is a very cool way of defining the area for the defining a vector for an area, because it's so easy to use in the future, even though it's look complicated at first. Okay, so this is what we have. So look at this two scenario over here. If you did what you just did before, but Ajahn, I still prefer to decompose the E to make it perpendicular to the area, right? So what you do is just, if you have the E, you just take the components that is perpendicular to the area. Is going to be E perpendicular is going to be E cosine theta. Does that make sense? If the angle between the E and whatever the line that they're drawing perpendicular to here is theta, so it's E cosine theta, right? And then what you do is the area of this surface is still A. So flux going through this one is going to be E. Here, let me do color coded here. So it's going to be E cosine theta times A, because this E cosine theta already piercing through this area in the perpendicular fashion as we want it. So perfect. You just multiply those. But once we define the area vector, I can do equally well with this. My A vector is already pointing perpendicular to the real area, right? So what I can do right now is I can break this into two components as well. So now this is going to be my A cosine theta, and I'm going to have this A sine theta up to the top right there. And do you see this? All I want is just the component of the A that is parallel to the E. By having my A vector parallel to the E vector, is guaranteed that the E is already piercing through the A in a perpendicular fashion. Does that make sense? Okay, one more time. Because we already defined the A vector to be the vector that actually points perpendicular to the real actual surface of the area. So by having the area vector parallel to the E is a guarantee that the E is already going through the area in a perpendicular fashion. Yes? One more time. We define A vector to be perpendicular to the actual area. So once we take the area vector that is parallel to the E vector, is a guarantee that the E vector must be perpendicular to the actual area already. Cool. All right. So with that, see, the flux that you get at the end is just, okay, let me write it as E times A cosine theta. And as you can see, no matter what you look at it, E cosine theta A or EA cosine theta, they are exactly the same. E cosine theta A or EA cosine theta, you get the same final value. But you have already done this once in your life, or maybe even more than once. What kind of operation that looks so close to something like this? Like E cosine theta A cosine theta E, cosine can be any way, blah, blah, blah. You sort of like remember this a little bit? Yeah, you did this back in the day of the work by the force. It's F dot S. Remember that the dot thing? Yeah. So what you have over here, as you say, is a Fs cosine theta. But of course, back in the day, you guys know that you can do F cosine theta S as well. It depends on you want to break or you want to decompose the displacement to be in the direction of force, or you want to break the force vector into the components that only pointing in the same direction as the displacement vector. It doesn't matter, but it's the dot products between these two vectors, the force and the displacement. Same thing over here. We just have two vectors. The vector that we are looking at is the electric field vector E, and now the newly defined area vector A. So what we just want these two to parallel, right? By having the E and the A parallel is a guarantee that the E is perpendicular to the actual area. So what you really want is, bam, here we go, guys.
Okay.
That's actually the complete definition of flux. It's just the dot product between these two vectors. You take the E, dot with the newly defined area vector, and it's guaranteed that you're going to get the electric field that piercing through the area in the perpendicular fashion as you want. So in conclusion, we define the area vector to be the vector having the magnitude equal to the area itself. So that's the A. But then you have that direction to be pointing in the perpendicular fashion. So sometimes they refer to as an N, the normal direction, with the hat. Remember, the hat is a unit vector. So whenever you have an area, all you have to do just, having that vector pointing, sticking out perpendicularly, and you take the magnitude of A and it's to the N hat. This is what it means. That is your A vector right there.
Okay.
Does that help? I hope. So this is something that I think it's new. It's annoying a little bit, but I think it's very doable. So for those of you that, sort of like get an idea, this will be the grand conclusion of what does it mean by the dot products between the E and the A. See, look sideways. It's going to be pretty easy to see. See, normal vector point perpendicular to the actual area A. And if electric field is pointing in this direction, now is your choice. You can break the E to be in the direction of N, or you can take the A vector, which is pointing in the direction of N, and break it down to the E, just like in the figure on the right. Does this help? All right. But understanding this one is another story. So this one is sort of like, okay, we get the definition down. We just say, okay, Ajahn, I got what you're saying. You just take the E vector, you do with the dot product with the A vector, and then whatever you feel like it, you just, find out what is the final products between the two. But to understand this intuitively, it will help much more. Okay, follow me this. Now, you probably caught me a little bit saying that, hey, Ajahn, when you have like a free floating area like this, And Ajahn, you said you need to have the vector defined to be in the perpendicular direction, right? But you said, but you have two directions, Ajahn. You can go down or you can go up. Why did you pick up? The reason is, yeah, as long as the area that you're talking about is an open area like this, you always have two choices to make. I mean, you have to pick one out of the two. It's either point in one way or the other direction, right? They're both fine. However, it turns out for us doing physics here, especially the Gauss's law, the surface that we are about to be dealing with is always be a closed surface. When you say closed, think of it like a balloon, like this one. It has to wrap itself. So that means that surface must containing some internal volume. Does that make sense? When you have just a free floating open area like this, there's no volume defined, right? Because it's not closed on itself. But once you have an area that closed on itself, it's going to wrap something up. So there must be some internal volume well defined. That's what it means by having a closed surface. So once you have that, there's no ambiguity anymore, because we only gonna define the area vector to be pointing outward from the internal volume. Cool? All right.
Okay.
It might not be that cool, but it's just a convention. It's there's nothing cool about it. So that means if you look over here, all right, you have like a elliptical balloon like over here. And then you can see that at the area number 1, so if I slice into a tiny piece, then the the area vector will be pointing, okay, let me do a black color here. It's gonna point perpendicular to it. That's what it is. Cool. If you look at the area number 2, it's just like at the bottom of this balloon here, the A will point perpendicular to it. Look at the number 3, it's toward the back side of this balloon. It's going to point backward a little bit, so that's fine. It's just going to point there. There you go, something like this. So that's what it is. Area vector always point perpendicular to, and now when you have a closed surface, it's going to point outward from the internal volume. So there will be no more ambiguity anymore. Area vector is already defined in the outward direction all the time. Okay, so with that, then now when you calculate flux, you're going to have 3 possibilities over here. Look at location number 1 again. The electric field vector is still pointing to your right, and the area vector is still point toward your right a little bit. So it makes a little bit of the angle, but the angle theta is still less than 90 degrees. So in this case, if you want to do flux on the surface, number 1 is going to be E dot A, but it's going to be EA cosine theta. And theta is still less than 90 degrees. No matter what you have, you're going to have a positive value at the end. Cool? Nice. On the other hand, if you look on the back side, area number 3, electric field vector is pointing to your right, right? There's no change. It's pointing to your right according to this figure over here. But then your area vector is now pointing backward. So what you have over here is your theta is going to be greater than 90 degrees. So when you do the flux calculation on this surface, it's going to be EA cosine theta, but now theta is beyond 90 degrees. You're going to get a negative number out of this. Cool. And another possibility is, of course, just in case that electric field is pointing to your right and area vector just accidentally perpendicular to it. So in this case, your theta is going to be 90 degrees. So EA cosine theta will definitely give you 0 because theta is definitely at 90 degrees. Cosine 90 is 0. And this makes perfect sense because when E and A are perpendicular to each other, it means electric field does not penetrating that area. There's nothing in or out. It is nothing. It's just going, it's just glance through the surface. It's just like, passing by. No going through. There's no penetration through the surface. Nothing. So at the conclusion over here, we have 3 cases. Electric field can give you a positive flux, negative flux, or no flux. But now when you look at this one, do you see what the flux is trying to tell you? Do you see that? You see that? Look on the right, the area number 1, flux is positive, right? This is a positive flux, right? It means electric field is coming out. Electric field is trying to escape from the inner volume. On the other hand, on the left side, flux is kind of negative. So it's like electric fields, it's trying to enter the balloon, it's trying to enter into the internal portion of this balloon. And of course, in the case of zero flux, I mean, it doesn't contribute to in or out. And that's what the flux means. And actually, this meaning of flux works in other area of physics or engineer and everything as well. Because you can imagine that this flux can be like a water stream. Think of it that way. And the balloon is like, you can think of it like a water container and stuff like that, right? And now, if you want to see about Ajahn, is the water level in the balloon is going to increase or decrease? You say, about Ajahn, how are we going to be able to calculate that? I said, look at the water's flux, right? Because positive flux means water is leaking out. Negative flux means water is leaking in. It's not leaking, it's entering the balloon. So if you net the in and out, you will be able to determine the level of the water in the balloon is going to increase, decrease, or no change. See, the flux sort of give you an idea of what is going on. But because this one we talk about the stream, so it's more like a rate of change. But the concept of flux is giving you the idea of things to change in the positive sense or negative sense. So it means you're going to get more or you're going to get less or you're not going to get any change. That's what the flux is trying to tell you. Another idea is probably could be heat flux. Yeah, it's like, okay, if the balloon is like a room and you have like a heat flux, positive heat means heat is being taken away from the room. The negative flux means there's a heat is entering the room. So if you net the net heat flux, you will be able to tell if your room is going to get hotter or cooler or no change. Does that make sense? But once again, heat is more like a dynamic stuff, right? Because it's flowing in and out. However, in our purpose in electric, it's more like a static in a sense that there is something piercing out and something just entering in. But anyway, the point is it still give you the direction that is that's out, that's in. So if you net them and there's nothing out or in, you can assume something. It's not happening inside or something like that. And that is the Gauss's law that we're going to conclude next time. But for this time, I hope you understand what the flux is trying to tell you. Okay, it gives the vector quantities. It gives you the relationship between the vector and surfaces. And also it gives you the directional in the sense that is that vector E is pointing in what direction? Is it pointing outward or is pointing inward relative to the closed surface that we have? Does it sound good? All right. So that's what you have over here. So that means once you extend this idea into a closed surface, so the natural question that you're going to get is, give me the net flux across a closed surface. So if you want to write things like in like you know more advanced stuff, that can be done easily using calculus. So you can slide this piece, slice your surface into a tiny piece, and I mean, if the piece is big, you can still call it delta. But if the piece is super duper small, you can turn it into an infinitesimally small area dA. Cool. And then what you do, you just take the electric field at that point. You dot it with the area vector. Don't forget this is still the area vector, yeah, even though it's small. So that means the flux going through this tiny piece, you can call it like a mini flux there, is just the E dot with the dA. Isn't that cool? Very nice.
Okay.
So with that E dot dA, that is the flux that is going through your tiny, super tiny area A. That's your name's dA. You're going to get a very tiny mini flux, D flux. But then you want all of these. So it means you just keep doing it, dA, 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 dA. And each dA, you're going to have your own, there's E here, E there, E at that location. You do E dot A, E dot dA, E dot dA, right? And then you sum them up. Once you're done with that summation, which is turned into integral because you do it infinitesimally, that is your net flux through that surface. Sounds cool?
Okay.
And not only that, because we already said we're going to keep our analysis only on the surface that is closed. So usually they will put an extra sign here just to emphasize that, hey, this is not going to be any area integral in general. It's going to be closed surface integral. The area that we are analyzing must be closed. And that's it, guys. This gives you the expression of flux through any closed surface can be done that way.
Okay.
Integral that's the. So I hope this not too heavy, even though it's kind of new and all this stuff, but I hope it's doable. All right. So just to give you like a qualitative understanding of this one, let's do this. What do you think the net flux will happen on this spherical closed surface? What do you think? Positive, negative, or zero? Don't need that. So what then? It looks like positive because every time that you slide a tiny piece of area, the dA will pointing outward, right? dA is pointing outward. And your electric field is also pointing outward. So no matter which area dA you are talking about, E dots dA always give you a positive value because tiny flux is going to be E dot with the dA, and it's just E times dA cosine zero. See? Because they are parallel already. Very nice. So no matter what it is, it's going to be positive. So I say this could give you positive net flux. Cool? Look at one in the middle. Well, Jan, look at this one. Well, you have three surfaces. You have the top surface, you have the bottom surface, and you have the side surface, right? Okay. The side surface, just forget about it. Flux on the side is definitely nothing. Because, I mean, you don't even have to do the cosine theta or anything. It's obvious electric field just pointing down. There's no penetration through the side surface at all. So there's no flux in, there's no flux out. Flux through the side must be nothing. So now when you look at the top, okay, well then the surface on the top, if you want to write the area vector is going to point upward because always point outward, right? Now, at the same time, the electric field vector is pointing down. All right, so at least you know that the net flux that going through the top surface must be negative because electric field is trying to enter the enclosed volume. Or think of it is theta is 180 degrees. So cosine theta is -1. Cool? All right, you get an idea. But then, now when you look down here, John, down here, electric field still pointing down, but now your surface area for the bottom surface is now pointing outward, which in this case is down. So your theta down here must be 0. So cosine 0 is 1. So you're going to get a positive flux at the end. But from the look of it, Jan, seems like the one that entered the top must leave at the bottom because the amount of light that coming in and the amount of light that go out seems to be exactly the same. The surface on the top and the surface at the bottom are the same. So the plus and minus flux that you got must be exactly the same as well. So that's why flux nets must be 0. Does that make sense?
Okay.
So I hope you start to get the feeling what does the flux is trying to tell you. It seems like, okay, on the first one, there is a net positive flux. So it's like something's leaking out from this sphere. Something just, exploding. I mean, it's not exploding. Something is like diverging out. On the second one, it seems like nothing. It's in and out. Electric field gets in and it gets out. So that's it. That's no nets. There's nothing left over inside the tank here. There's nothing in this cylinder. There's nothing left in there. And that is going to be the same thing on the right. Even though you change the configuration into a cube. But from the look of it, Ajahn, well, there will be 6 surfaces, but the only surfaces that have non-zero flux is going to be the one on the left and the one on the right. But whatever that comes in, electric field that piercing into the cube on the left, it actually is going to exit on the right. So you probably can guess the net flux over here is also zero. Get an idea? And when you say that, it's like, okay, there's nothing in the box. In the box, it doesn't really have anything net because net is zero. So I hope you see the contrast between the case number one, you have a net positive flux. Number two and number three, you have net zero flux. Okay, got sort of like an idea of what this is, okay? So with that, then let's do some quantitative calculation, all right? And I think you will get better understanding of this. Okay, so let's give it a shot. So I think I'm gonna show you maybe 2 exercises today, and I'll just leave it at that. And next time, I'm gonna go up to a more advanced geometry, and sort of like, I think I need you to have this concept sort of sink into your head first, and then you have to think about it for a while. And once you know being hit again with this material, it's just like maybe there's a something light bulb moment coming up. I hope.
Okay.
All right, so try this one. All right, so we're gonna do 2 exercises here, a simple ones, of course, and I hope that will clear things up just a little bit further. Consider a uniform electric field E oriented in the X direction. All right. Now find the net electric flux through the surface of a cube with the edge length L, oriented as shown in the figure. All right, done. This is not bad because it's just a cube. So what we can do is we can define the area vector for all. You have a total of 6 surfaces: the top, the front, the left, the right, the bottom, and the back. Cool? All right, so what I can show you right now is, of course, the net electric flux must come from flux number 1, which is what they define. Number 1 is on the back side, or let's call it the left one. That's number 1. Flux on the top, which is number 3. Okay, let me write it here. Top, okay, front, back, bottom, and the one on the right, that's named number 2. Sounds good? All right. So from the look of it, Marjan, without any calculation, definitely the one on the top will give you no flux. The one on the bottom as well, the front and the back. The reason for that is because you can see right away that electric field does not penetrating those 4 surfaces at all. Sorry. See? There's no penetration through these 4 surfaces. So forget about those. The only thing that you need is just the surface number 1 and surface number 2. So let's focus on that. So let's start on that number 1 surface there. So the area vector is going to point backward. You guys with me here? There. So the area vector is going to point, okay, let me highlight it in the red one here. That's the area vector is going to point backward, while the electric field vector is pointing forward like this. That's electric field vector. So what I can write down right away is flux on the surface number 1 is going to be A1. Okay, let me do it in order here. Is going to be E dot with the A1. You don't need to do any calculus at this point because it's just a flat surface without, they're all oriented in the same direction. So you can say it's just A1 pointing backward. Okay, so what I say over here is A1 is just L square minus I. You get that notation here? Just for those that are familiar with this, the reason is because the size of this area is L square, the width times the length, and it's pointing backward in the sense that it's going in the negative X direction. So that's why I put a negative I right there. So electric field itself, I can write it as an E times I hat because it's pointing in the positive X direction. So that's it. I can just do E I hat dot with L square minus I hat. Or for those of you that don't like this notation over here, you can just say, Ajahn, it's just EA cosine 180. So I hope this give you the equivalence between two types of notations, right? You can do EA cosine theta, or you can do the the unit vector notation. They're all the same. So with this, all right, no matter what you do, is negative EL squared. That's for the flux through the surface number one. And you do the same thing for the surface number two. On the surface number two, let me highlight it in blue. Your area surface now is going to point in this direction. That's A2. And you can see now it's L square I hat, because now it's pointing in the positive X direction. Or if you think in terms of the theta is 0 degree. So what you can do is flux over here is going to be equal to the E dot with the A2. It's just E A cosine 0. Or you can say is the E in the I hats dot with the L square with the I hats. Same thing. No matter what you get at the end, you're going to get positive EL squared. And you can notice right away that, hey, that it's a negative and positive here. They eventually going to get canceled. And hence, what you get at the end is just net flux is 0. And you are done.
Okay.
As expected, right? Because we already discussed this. Well, of course, that. All right. It's supposed to be 0 because what is entering is leaving the box or the cube over here. But this one, we're going to do it quantitatively. Right? Just showcase exactly what is going on the left side of the box and the right side of the box. What enter exits the box. Cool. All right. Seems like there is smaller number of people toward the end of the course right now. You still have some energy left, right? One more. Last one, guys. I know. Oh, I know it's been it's 3 years. Oh my God. Teaching online. It's just taking a toll right now. And eventually I got COVID anyway. So after being careful so much, so many years, toward the end, almost, we gotta open up the campus and everything, and it got COVID. So, all right, guys. So try this as the last one. All right, I think this is going to be the most complicated one of the day. Okay, of flux calculation, but I hope it's not that bad. Okay, so consider a closed triangular box resting within a horizontal electric field. Once again, electric field is pointing horizontally. The magnitude is given. Calculate the electric flux through, okay, they want to do it in steps: the vertical rectangular surface, the slanted, and the entire surface of the box. Okay, so let me attack the vertical rectangle first. Here we go. I'm highlighting this in green. And there you go. All right, so I think maybe it's easiest to look sideways as well. That will help. Okay, so let me draw this triangle. So this is side view. So your electric field is going in this direction here. And as you can notice right away, area vector for that vertical surface is pointing backward. You guys with me? So if I overlay on top of this, this is your area vector is going to point backward like that. Cool. So right away, you can say about John, oh, it's 180 degree angle with each other. Electric field vector and the area vector, they are pointing in the opposite, opposite direction. Cool. So over here, what I can write right away, just saying that A, flux through the vertical surface, let me put the subscript V for that, is going to be E dot A vertical. So let me put the subscript V for that as well. And now you know it's going to be E magnitude, some magnitude of the vertical area, and cosine 180 degree. Cool. And everyone can expect to be a negative flux because electric field is trying to enter the internal volume here of this triangular box. Okay, what is the size of the vertical area? No big deal. That is just this surface right there. So the A vertical is just 0.3 times 0.1 put in SI system. So it's 0.03 meters squared. And that's it. All you have to do is just plug in. So cosine 180 is negative. Electric field is 10 to the fourth. Area vector is 0.03. Let me omit the units for now. And that's what it is. Okay. So that's not bad. That's not bad. Now let's do part B. Well, that part B is sort of about the same, except now your area vector is going to point perpendicular to it. I think maybe I want a little bit bigger than that. Okay, here we go. So for the slanted surface, so let me do it in blue. Let me call it A sub S. Okay, and every time we draw this, we draw a perpendicular direction to the actual area. Now, what kind of angle that the area vector S make with the electric field? Okay, so that's the theta that we want, right? But from the look of this one, they already said it gives you 60 degree on this angle over here. So this is 60 degree. So if that is 60 degree, so this is going to be 30, this is 30. So actually theta is also 60 degree. Perfect. So now we should be able to calculate flux through the slanted surface. So let me put S there. So it's going to be E times A sub S. And the A sub S is just this huge, big slanted surface right there. Let me highlight it in blue. There you go. All right, so that's A sub S. So whatever it is, it's going to be E times A sub S cosine 60, right? Almost done. The only thing left for you to calculate is what is the A sub S? Well, John, it's just the width times the length. The width is already known to be 30 centimeters as well. That's no big deal. Okay. But the length that you want is going to be this side right here, right? This hypotenuse over here. This is what you want. So let me call this S for now. So something is about to happen here. So the A sub S is just going to be S times 0.3, right? That's the surface area of the slanted surface, right? So I plug it in. I get S times 0.3 times cosine 60. Do you notice something here? What is S? Well, Dan, I can calculate S. That's no big deal. But what is S cosine 60? Oh, Dan, actually S cosine 60 is this length over here. You guys with me here? If you look at this right triangle, S is hypotenuse here. The height over here is S cosine 60. S cosine 60 is actually 10 centimeter. It's the vertical length right there. Okay, yeah, that's nice. So that means it's a E times 0.3. S cosine 60 is 10 centimeter, 0.1. Uh-oh. And it's exactly positive 10 to the fourth, 0.03. And you can notice, well, John, they are exactly the same number, except one is negative, one is positive. We knew that because first vertical surface negative because electric field is trying to enter. But on the slanted surface, electric field is trying to going out. But when you look at this one carefully, in is equal to out because every electric field lines that enter exits this triangular box. And I just shown you here. It's been shown here that, yeah, whatever the flux that enter in part A equal to the amount of flux that actually exiting in part B. And now, if you want to lead, if you lead to part C, what is the entire surface of the box flux? For Ajahn, it's no big deal because flux on the front surface, this is 0. Same thing with the flux on the back surface is also 0 because electric field do not penetrate the front and the back side surface at all. So you can say that net flux is on that.
Okay.
All right. So I hope that if you go back and review this one more time, I think this is sort of like the very, this is the peak of the flux material over here. This is it. Okay. If you understand this, and next time I'm just gonna add something a little bit to it, then understanding Gauss's law is gonna be super easy. Okay. And if you go back and review this one and make sure that you understand what is trying to do, that it means the dot product between E and A to get to the flux. What does it mean? The next time, I'm going to attach this to something that, once again, mathematics, they already had this kind of operations. And I hope that we can intuitively understand what the flux is trying to give you, what kind of information that you're supposed to be able to gain from flux calculation. And once you hit that understanding, bam, Gauss's law is waiting for you. Cool? All right, guys. So I think that is it for today.
Okay.
Thank you very much for sticking around, guys. All right, stay safe. I think, yeah, my running nose is back. All right, guys. Thank you. I'll see you guys next time. All right. So, just watch out for the makeup. Okay, I'll let you know when. Okay. Bye bye. Take care. See ya.